All right, let's review arrow notation, and also we're going to talk about vertical and horizontal asymptotes here. All right, let's just look at these graphs. These are toolkit functions. We have f of x equals 1 over x, f of x equals x squared. These have some notable things happening, right? So we notice that at 0, both of these functions aren't defined, right? In this one, the graph kind of shoots up and down. And this one, the graph shoots up on both sides, right? We're going to learn that those are called vertical asymptotes. And we also notice that as we go, the end behavior of these functions isn't going all the way up or all the way down. It looks like it's getting close to the x-axis in both cases. And we're going to call those horizontal asymptotes in just a minute. But until then, let's think about mathematically how we can describe this, what I called like shooting up, right? Shooting up or shooting down, or getting close to the x-axis. We're going to have to use arrow notation. So let's just review this. So we have some symbols. We say this x approaches a, and then we have either a plus or minus as a little like exponent kind of thing, right? This means approaching a from the left. This means approaching a from the right. So here we have x approaching infinity or x approaching negative infinity. And here's the function itself approaching infinity, or the function itself approaching negative infinity, or the function itself approaching a. Okay? So this little arrow, we say approaching. So x can approach a number from the left or right. It can approach positive or negative infinity. And the function itself can approach infinity or negative infinity, or it can approach a number, like 4 or something. All right, so let's look at this graph of 1 over x and think about the arrow notation. So as x approaches 0 from the right, on this side, as x approaches 0 from the right, what happens to the graph? F of x approaches infinity. And as f of x approaches 0 from the left, right, with this little negative sign, f of x approaches negative infinity. How about here? As x approaches infinity, f of x approaches 0. Doesn't never get there, but it approaches 0. And as x approaches negative infinity, f of x approaches 0. All right, so a vertical asymptote of a graph is a vertical line, x equals a, where the graph tends toward positive or negative infinity as the inputs approach a. Right? So as x approaches a, f of x approaches infinity, or as x approaches a, f of x approaches negative infinity. And it could be different, right? It might be different if we're approaching from the left or the right, as it is in this case. So again, just as a review, here is our vertical asymptote. The vertical asymptote is at x equals 0, and as x approaches from the right, f of x approaches infinity. As it approaches from the left, f of x approaches negative infinity. A horizontal asymptote is a horizontal line, here the green one, where y equals b, where the graph approaches the line as the inputs increase or decrease without bound. Right? So that means as x goes to positive or negative infinity, f of x approaches b, so the value y on the y-axis, the line y equals b. All right, so let's practice this. Use arrow notation to describe the end behavior, meaning as x approaches positive or negative infinity, and the local behavior of this function. All right, as x approaches, so we're going to have, before I show you that, let's just make some observations. We have a vertical asymptote in red at x equals 2, and a horizontal asymptote in green at y equals 4, right? So as x approaches 2 from the left, f of x approaches, as x approaches 2 from the left, f of x approaches negative infinity. And as x approaches 2 from the right, f of x approaches positive infinity. And how about the end behavior for this horizontal asymptote? As x approaches infinity, f of x approaches 4. And as x approaches negative infinity, f of x approaches 4. All right, let's do another example. Sketch a graph of the reciprocal function shifted 2 units to the left and up 3 units. Identify the horizontal and vertical asymptotes of the graph. All right, well, we can use our transformation of functions knowledge. Right here we have, so the original graph would be 1 over x. X plus 2 means it shifted to the left by 2. And plus 3 means it shifted up by 3. Okay? In this section, we're going to be talking about rational functions. So let's rewrite this as a rational function. We have this term and this term. If we had a common denominator, they would look like this, right? If we wrote this as 3x plus 6 over x plus 2, and then added the numerators, we'd get 3x plus 7. Okay, think about that if that's not kind of clear to you, how you do that. Okay, so here we have what we call a rational function. We have got a polynomial on top and a polynomial on the bottom. And the asymptote, so the graph itself is just shifted, right? It's not stretched or anything. So the whole graph has moved up 3 units and over 2 to the left, right? And the horizontal and vertical asymptotes also have moved, right? We had a vertical asymptote at 0. Now we have a vertical asymptote at -2. We had a horizontal asymptote at 0, and now we have a horizontal asymptote at 3. And if we wanted to describe that using arrow notation, as x approaches -2 from the left, f of x approaches -infinity. And as x approaches 2 from the right, f of x approaches infinity. And we could write this in one statement: as x approaches positive or negative infinity, f of x approaches 3. Okay, so we are going to talk a lot more about vertical and horizontal and other kinds of asymptotes in the next section.